Well, hello folks. Back again for the second video, and I hope that the lesson from the first video, at least the homework problems that you had to do, turned out pretty well. Give me an email if you're struggling with anything. If you find that there are large areas of confusion, you probably want to talk to me very quickly, first day probably, so we can decide what we need to do to take care of your situation. But today what we're going to do is take a look at two sections in the book. We're going to wrap up chapter 1, and our topics are going to be continuity of a function and then infinite limits. So section 1.4, we're going to focus on continuity, and I believe most of these concepts, if not all of them, are going to be familiar to you. Right, we're going to begin with the continuity of a function at a point. Okay, so the definition of when a function is considered continuous at a certain x value is if f of c is defined. In other words, you have to have a function value at c. And then, is there a limit for that function as x approaches c? Of course, that entails that the left-hand limit and the right-hand limit agree with each other. They're equal to the same finite number. And then thirdly, will that two-handed limit, as x approaches c, actually equal the function value itself? And so actually, it's this last section that pretty much covers it, because if you're going to have a limit, and you're going to have a function value and they equal each other, that's pretty much what we're saying in the third part of that definition. Okay? Now, we're also going to talk about continuity over intervals, and we're going to begin with an open interval. So we say a function is continuous on an open interval if the function f is continuous at each point in that interval, or in other words, at every value of c within the open interval. So you can say open interval represents, continuity on an open interval represents the function being continuous at every c value within the open interval. Okay. Now, before we look at closed interval, let's just step back and talk about what we're, what would be examples of discontinuity, or where the function is not continuous at a point or on an interval. Right? Now, there are three basic types of discontinuity, and they don't necessarily have to be in this order, but as I think of discontinuity, one type that I think of is what we might call jump discontinuity. That is where your function is made up of two pieces where they're not joined, if you will. There's a disconnect. So say from A to B, that would be an open interval where the function that I've graphed is not continuous because there is some c value within the open interval where the left-hand limit doesn't equal the right-hand limit. So it fails the definition of point discontinuity for that reason. There is a function value at c, but we don't have a limit because the left and right-hand limit says x approaches c do not agree. So this is what we would call jump discontinuity. All right, now a second type of discontinuity, that's a little slanted there, would be something like this. Now, the problem here isn't that the limit doesn't exist for every single point in an open interval, and let's say the open interval goes from A to B. You see, where we have this point discontinuity, this missing point along the path of this curve, The left-hand limit does agree with the right-hand limit. The problem is the function value doesn't exist, right? So point discontinuity. Now, an interesting variation here, which could be considered point discontinuity as well as jump discontinuity, is if we come up with a function value at C somewhere so not to actually plug the hole, if you will, but we have a point somewhere else. So again, we would have a function value that doesn't agree with the limit as x approaches C. And so it's still considered a discontinuity. Right? And then the last of the three would be infinite discontinuity. And this is where you have a vertical asymptote. I don't know why I said 3. It doesn't have to be 3, but say x equals C. Right? And so let's have a function that might look something like this. And there's our interval from A to B. So there is not point continuity at x equals C. Therefore, there is not open interval continuity, or the function is not continuous from A to B in the open interval. Okay, so we call this infinite discontinuity. Now, of these three discontinuities, one of them will be referred to as removable discontinuity. Right? Now, the idea behind removable discontinuity really amounts to being able to plug a hole. Right? If you can redefine your function so that f of c is declared to be just the right y value so that you can connect the pieces of your function so you don't have the discontinuity anymore, we say, hey, that's a removable discontinuity. Now, there's only one type of discontinuity where that would apply, and that's the point discontinuity. You see, that missing point can be plugged by just saying, let's let f of c equal just the right value. Let's say that's a d, just the right value so that we do plug the hole. Now, if I already had f of c equaling something else, then I would have to redefine it. If I didn't have an f of c, then I am just introducing that as an additional condition on my function rule. But removable discontinuity can be thought of as point discontinuity because you can plug the hole by adding a condition to your function. Okay. All right. So let's wrap up these types of continuity with the idea of continuity on a closed interval. Now, the issue with a closed interval is you can't have point continuity on the ends of an interval. Now remember, continuity on an open interval required that we had point continuity for every single c value within the interval. But if we go to a closed interval, suddenly the ends of the interval, the a and the b, are now possible choices for c, and we would have a problem here if we held to point continuity definition, which says your left and right hand limits have to agree so that you have a limit as x approaches a from either left or right, and it equals the function value at a. So we just make a little bit of an adjustment for the closed interval situation. All right, we're going to say that, look, over on the left hand end of our closed interval, we're only going to require that there is a right hand limit and that it agrees with the function value for a. And then way over on the right end of our closed interval, we're going to just make sure that the left hand limit agrees with the function value over there. So an example, just to make sure you get this, it's not really that hard, is f of x is equal to 25 minus x squared. Now this is a parabola, or at least part of a parabola, where we're going to get something like this. Okay. Now, if I decide that I want to have, instead of the whole parabola, I only want the part of the parabola, say from -5 to 5, say that's my interest here, then I don't see any breaks. I don't see any holes or jumps or infinite discontinuities. Over here at -5, the right-hand limit, as x approaches -5 from the right, the y value approaches 0, and that is the function value for f equals f of -5. Okay? And so that's going to fit, that's going to fit the requirements for being continuous on the left edge of our closed interval, if you will. So I'm trying to squeeze this in here. And then over here, likewise, the limit as x approaches 5, that's the rightmost x value. As we approach that from the left, this one we're actually approaching from the right, as we approach 5 from the left, we're going to get a limit of 0, which is equal to f of 5. Okay, so we would say that indeed this function is continuous over that closed interval. In fact, because of the nature of a parabola, you could have picked any closed interval and you would have had continuity. All right. Now, here's an example of the type of problem that you might run into, just to check to see if you really understand the definition of continuity. And I took this out of the book, page 80, number 58. And it says, find the constant a such that the function is continuous on the entire real line. That means real number line. Okay? So we need to make sure that there are no discontinuities anywhere for anybody. All right? Now, if we look at the pieces individually, this particular function, 4 sine x over x, only has an issue at x equals 0, but we don't have that as a part of our definition for the function for that piece. So for x is not equal to 0, we're not going to have any problem getting an output. So there's no discontinuities for x less than 0 for our piecewise function here. And likewise, a being a constant, minus 2x is just a linear function. That's not going to have discontinuities anywhere, let alone for x is greater than or equal to 0. So the real issue is, will these two pieces connect, or will there be a jump? Okay, so we only have to check for point continuity at x equals 0. So let's check to see what the limit is as x approaches 0 from the right. Now let's see, from the right, that means x is greater than or equal to 0. And I'm going to see if that equals the left-hand limit. Now as we come from the left, we're talking negative values for x. So I would be looking at this right here. And then both of those one-handed limits have to equal the function value at 0. All right, now out of those three expressions, I should be able to build an equation to solve for a. Right? Now, I know that g of 0, if I go to the piecewise function, again, this is the rule I would have to use for g of 0, and I would get a. Now the limit as x approaches 0 from the left of 4 sine x over x, Well, this piece right here looks very familiar. We just had that in the last lesson. Right? That's going to go to 1, whether it's a left-hand limit or a right-hand limit. And so the limit for this expression in the middle is just going to give us 4. And we can pretty much stop, well, we can stop right there. We just figured out a has to be 4. If we were to continue on, the limit here would be a, and so the value that we're looking for is 4. Pretty easy problem. Now you might get one on the homework where there's actually an a and a b that's missing, and you'll have to use this same sort of extended equation that set up possibly 2 equations, 2 unknowns, in order for you to find the 2 variables, or the 2 unknown constants, really, that you're seeking. All right, so I'll be looking forward to see how you do on that problem. All right. Now, to finish off the continuity idea is this important theorem called the intermediate value theorem. And the intermediate value theorem is really a guarantee that if a function is continuous on a closed interval, then that function has to achieve any function value between f of a and f of b. All right? You can't skip output values between f of a and f of b if you're not going to have any breaks in the function. Right, so here's my interval from A to B, and so this point right here would be the point whose x-coordinate is A, and there's f of A. There's the point whose, and I keep messing with my shadows here, but hang in there with me. There's the point whose x-coordinate is B, and there would be f of B. So according to the intermediate value theorem, I have to be able to find somewhere along the x-axis in the interval from A to B some input, at least one, that'll produce any of the outputs between f of A and f of B, no matter which one I decide to go for. Okay? So let's say the k that I'm shooting for, that's between f of A and f of B, is right here. And let's draw a horizontal line. Well, it seems in this example that there's more than one input that'll produce that output. So this could be a C, let's call it C sub 1. That could be a C, call it C sub 2. And that could be a C. So here, there are 3 possible values for C such that, that's the symbol for such that, f of C equals k, as guaranteed by the mean value theorem. Now, it's a big deal that we understand that the precondition was you had a function that was continuous over the closed interval. My mistake, I wrote some parentheses here. I should be using brackets. Okay. The reason you have to have closed interval condition is because it may turn out that the function value that you grabbed was actually f of A or f of B, and in order to get the output f of A or f of B, you may need to use A or B in there. So anyway, if you don't have the precondition that the function is continuous, well, now all guarantees are off, because I've drawn a picture of a function that has jumped this continuity in my interval from A to B, right here. And here is f of A. Here might be f of B. Now, I'm not saying that you can't find a C value for the output or function value that you're looking for, but you might not be able to. For instance, if we decided That's the value that we're going to try to find an input for so that the function produces that output. We're going to be out of luck. We can see that there are no, let's see if I can write that out. There are no values C such that f of C equals K here. Okay. Discontinuity causes this to happen. Okay. All right. So it looks like that's about all I wanted to do out of section 1.4 with the continuity and discontinuity idea. Yep, hold on. But you can't plan for announcements. Now, let's look at our last section. Infinite limits. Now, what we mean by infinite limits are functions whose limits as x approaches a certain constant would be infinity or negative infinity. All right, I want to begin with the function you see here. And if we decide that we want to take the limit here as x approaches 4, well, you might recognize you're going to have some trouble here because plugging 4 in will give us 0 in the denominator. All right? And so obviously our function's got a problem at x equals 4. So what you've learned in the past is to take a look at the factors that are involved in your function rule. And I'll factor the numerator and factor the denominator. And from those factors, you could talk about things like point discontinuity, infinite discontinuity. Right? Now, the fact that x minus 4 reduces to 1-to-1 ratio, and there's no longer a factor of x minus 4 in the denominator, that tells us that we have point discontinuity. Now, let's move this out of the way. At x equals 4. Right? And we'll take a look at the graph in a minute here. But let's look at the reduced function rule. Okay. If I decide I want to take the limit of f of x, well, direct substitution would have given me some trouble because as x approaches negative 4, I would have ended up with a 0 in the denominator, but I would have been all right actually with the numerator. I would have gotten a value of negative 2. So this is not that indeterminate form, that 0 over 0 situation that we were running into in the last lesson. This is a little different. As x approaches negative 4 from the left, the numerator approaches negative 2. Now I can figure that out by actually just substituting negative 4 in for x. Right? But the denominator approaches 0. Well, that's not so bad, because if the numerator approaches a constant while the denominator approaches 0, your ratio is getting ever larger. In other words, your ratio is approaching a magnitude of infinity. The question is which one? Is it going towards positive infinity or negative infinity? Well, based on the way I wrote those arrows, you would think, well, I've got negative 2 being divided by an ever smaller amount, so I must be getting ever larger negative values. But hold on, I wasn't being too careful here. As our function or as the x values approach -4 from the left, x plus 4 is always going to be negative. As x approaches -4 from the left, we're talking about values whose magnitude is a little bit greater than 4. So x plus 4 is always going to be a little bit negative. So even though x plus 4 approaches 0, it'll be approaching 0 from the left, meaning that our function is actually going to represent a negative number divided by a negative number. So even though the magnitude of that ratio is getting infinitely large, it'll get infinitely large in the positive infinity direction. Okay? So in other words, the function is going to be rising as we approach x values of -4 from the left. Now, if we do the same kind of thing from the right, what changes? Well, not much. The x plus 2 piece will still head towards -2. But now, as we approach -4 from the right, we're talking about values of x that are slightly greater than -4. Right? Therefore, the difference will always be positive, even though we're approaching 0. So this limit will get infinitely large in magnitude, but heading towards -infinity. Now, this behavior, as x approaches a constant, the function values get infinitely large, indicates that we're going to have a vertical asymptote. Right? And you learned in pre-calc that in your simplified function rule, back up here, in your simplified function rule, any values of x that would cause your denominator to equal 0 and help you locate where your vertical asymptotes are. So x equals -4 is where we would expect the vertical asymptote. And that's what our limits are showing us. Now, I'm not expecting you to find vertical asymptotes any differently in these rational functions than you did before. I'm just trying to show you what we're learning when we run into certain situations in our limit work. All right. Now, let's do a sketch of this function and pull together a couple of pre-calc ideas while we're at it. We got to point this continuity at x equals 4. So what you can do to figure out what point is missing, and I shouldn't call it f of x because it's really not exactly the same function. A lot of times we'll put a little bar down here saying, here, this is what we're plugging in for x. And we'll get 6/8 and 3/4. So at 4, 3/4, there's a hole in this graph. Say there's 4 and 3/4 is pretty tight to the origin. There's a hole. Now, the other thing that we learned with these rational functions, that's a polynomial over a polynomial, is how to recognize a horizontal asymptote. Right? And that was all about recognizing the ratio of the highest powered terms. So if we look back up at the original function rule, grab the highest powered terms top and bottom, we can say that the limit, put this down towards the bottom, the limit as x approaches infinity of f of x would be the same as the limit as x approaches infinity of this ratio of x squared over x squared. Well, that reduces to 1/1. And we know the limit of a constant is the constant regardless of what the x value is approaching. So at 1, we have a horizontal asymptote. So let me jot that in there. Y equals 1. And we have enough really to do somewhat of a sketch. I guess we could purpose to figure out what the x-intercepts are. So let's go back up and do that. X-intercepts would be those values of x that make the numerator equal to 0 in the simplified rule. So at -2, we have an x-intercept. Okay? And that should just about do it for a graph. One of the things that we learned, hopefully, in pre-calc, and I keep saying hopefully because I wasn't there with you, but one of the things I expected you to learn is that when you determine where the x-intercepts are, you're also determining where they are not. So since -2 is the only x-intercept for our function, there are no other x-intercepts. We can use that to help us in determining the curve of this function. As I scan from the right of my graph and move left, which is counterintuitive, but that's how I'm going to do it this time, I should be coming in off of the horizontal asymptote, going to the hole. Don't really go through it, but to the hole and then back out the other side and keep on going until I hit -2. That's where I cross. And then I come down and start pushing up against the vertical asymptote. And you'll notice that our work tells us back here that as x approaches -4 from the right, we do expect the y values to head to -infinity. Right? Now, as we head from left to right, there are no x-intercepts, so I'm going to have my graph coming into the horizontal asymptote from above. It's not going to be crossing the x-axis at all, and I will have to push up against that vertical asymptote by heading towards positive infinity. And so there's a little bit of a review of some of the graphing techniques that we have used and how it might relate to what we're going to talk about with these infinite limits. All right, so let me just take a quick breather. All right, let me wrap up by showing you some properties of infinite limits, and we'll do a handful of problems, and then we'll be done here. All right, so I'm going to give you some properties that we can use when working with limits that go to infinity. And each of the properties is going to rely on the given information that I have written here. First, the limit as x approaches c of f of x is going to be infinity, okay, for all the rules I'm about to give you. Whereas for g of x, it's going to be some constant value, okay, some real number value, not infinity. And also, whenever you see c, that's going to be another real value, a real number, some constant value. Okay? Now, the first one, if we find ourselves trying to take the limit of a sum of two functions, and one of the two functions, let's say the first one, heads to infinity, while the second one on its own heads to a constant, we can use the idea that the limit of the sum is the sum of the limits. And the first limit will be infinity, and the second limit will be the constant value L, the sum of which in the limit world is still heading towards infinity. Okay? And in fact, if there's a difference between these two functions, the first function heading to infinity is going to overwhelm the second function's limit, which is a constant, and that difference will again be a difference that heads towards infinity. Okay, so there's one property. A second property, and these are modeled after the limit rules for finite limits that you used last year. If you have the limit of a product, we often said, well, let's just do the product of the limits. And you're pretty much doing that here. The limit of f of x is infinity. The limit of g of x is the constant L. So the product of an amount that goes to infinity and an amount that heads towards a constant is going to be an infinite amount. It's just we have to decide whether we're going to positive infinity or negative infinity. You see, if g of x is heading towards a negative number, then the product infinity times a negative number will always be negative, even though it's getting infinitely large. Right? And that's this case right here. But if g of x is heading towards a positive constant value, then we know that the product is going to be a positive, even though it's increasing in magnitude infinitely, and that's that first case. Okay, now notice back here, we didn't care whether g of x was a positive or a negative, or heading towards a positive or a negative value, because it's being added to infinity, and the infinity part of the sum is what decided where that sum was going, or the difference. Okay. Let's look at the third one I have here. This is really the first of two quotient rules, where one of the functions is heading to infinity and the other is not, is heading to a constant. Remember, f of x was heading towards infinity, whereas g of x is heading towards a constant. Well, in the sense of the magnitude, if the numerator grows without bound, but the denominator heads to a particular constant value, then the ratio is increasing without bound in magnitude. The question is it heading towards positive infinity or negative infinity? Right? So if L is a positive number, then we would be looking at a ratio of positive numbers that increases in magnitude, and so we would head towards positive infinity. But if L is a negative number, then we're dealing with a ratio of numbers with different signs, so we'll always have negative ratios, and therefore we're going to head towards an infinitely large amount, but negative. Okay. If we flip-flop these and say g of x is in the numerator and it's heading towards a particular constant as x approaches c, and f of x is getting infinitely large, now it doesn't matter whether L is positive or negative, that ratio will get infinitely small. It heads towards 0. All right. Now, these properties, which I've given to you, all assume that f of x was heading towards positive infinity. Now, we can rewrite all these properties again. I don't really want to do that. But let's just quickly look at what would happen to our rules if f of x were actually heading towards negative infinity. So now I would have in this first rule the limit of a sum of functions where one goes to negative infinity and the other goes to a constant. Well, I think it's pretty clear that the sum will head to negative infinity, and so would the difference here. So we would just get negative infinity there. On number 2, if I have a function heading towards negative infinity and another function heading towards a positive, say this were positive, then the product would be negative here, but if the constant that g of x approached was itself negative, I would have a product of negatives and I would get a positive, right? So we can do the same kind of thing all the way through. So the principles behind our decision making is what's important here. We don't need to make sure that we've memorized 15 variations of these principles. Now, can we apply these principles to these problems? And this will be all we need to do today. We'll just do these 5 and we'll call it a summer. How's that sound? All right. So the first one, the limit as x approaches 1 from the right of 2 plus x over 1 minus x. Well, first thing, check direct substitution. Whenever you're doing a limit, always check direct substitution, because if you can get away with that, that's what you want to do. Now, if I do direct substitution, I'm going to get 3 over 0. All right, that's not an indeterminate form, so I don't have to go to one of these methods of reworking the function rule so that I can do direct substitution. right? What I want to do is try to look at where the pieces of the function will go and see if I can't just reason this out. For instance, the numerator will head towards 2 plus 1, which is 3. The denominator will head towards 0. Now, careful. Will it be heading towards 0 with positive numbers, or will it be heading towards 0 with negative numbers? Well, heading towards 1 from the right means we're going to be looking at x values slightly larger than 1, meaning that the difference is going to be negative. So we're going to say, oops, sorry, we're approaching 0 from the left, or with negative numbers. Whenever you approach 0 from the left, you're approaching with negative numbers. And so the ratio here will produce a negative ratio. But because the denominator is diminishing in magnitude, heading towards 0, while the numerator is locking in on a constant, we're going to get an infinitely, or we should say a ratio that is growing infinitely large in magnitude. So we'll write negative infinity there. Okay. Now this next one, the limit as x approaches 3 from the left of x squared over x squared minus 9. It looks like it ought to be fairly easy. Let's see what happens here. I'm a little concerned about the x squared minus 9 because there's a couple of factors there. So let's break it up just in case. Okay. It may turn out we didn't need to, but I'm going to go ahead and do it anyway. Well, as x approaches 3, x squared will approach 9. No problem there. As x approaches 3, x plus 3 will approach 6. And then x minus 3 will approach 0. Ooh, but anytime we're approaching 0, and we don't have a 0 over 0 situation, we're going to have to decide whether we're approaching 0 from the left or the right. So it looks like as we approach 3 from the left, x minus 3 is going to approach 0 from the left. And so we're really looking at 9 to something approaching 0 from the left. Okay, which is really negative infinity again. Now, all right, without the factorization, we could have come up with the same thing. You see, if we approach 3 from the left, that means x squared is approaching 9 from the left. In other words, numbers that are slightly less than 9. And that would have allowed us to indicate that that denominator is approaching, 0 from the left. Let me rewrite that. Whereas the numerator approaches 9. So that factorization really wasn't all that important. All right, number 3. Well, I have a limit of a difference, and the first function, x squared, goes to 0, and the second function goes to, well, if you just consider this piece goes to infinity, but is it negative infinity or positive infinity? Well, as we approach 0 from the left, we're using negative numbers for x, which means 1 divided by a negative number is going to be a negative ratio. So we can argue that this looks like a 0 minus a negative infinity situation, or infinity. Okay. All right, 2 more here. We have a limit of x plus 2 of cosine x as x approaches pi over 2 from the left. I don't know if you can see that. All right, well, direct substitution here again gives me a 0 in the denominator. Now, in the numerator, I'm not going to really worry about working out exactly what number that is, but pi over 2 plus 2 is clearly a positive number, right? And that's really all I need to know there. It's going to approach a positive constant. The denominator is going to approach 0, but is it approaching 0 with positive numbers or negative numbers? Well, I'm going to be careful with this one. Let's see, where's the cosine curve, right? And as we approach pi over 2 from the left, we are approaching y values of 0 from above, or positive values. Okay? So the cosine of x is closing in on 0 with positive values. So a constant in the numerator over a denominator that approaches 0 is going to be infinitely large, and we have positive divided by positive. All right. Now, last one, the limit of 2 over cotangent x as x approaches 0. Now, if you go to plug 0 in for x on this last one, the cotangent of 0 is undefined. So we can't do what we did in number 4, where we just said, hey, look, we've got a constant up top, and the denominator we're heading towards 0. Because in actuality, x actually approaches either infinity or negative infinity, depending on which direction we approach 0. Let's take a look at the cotangent curve so you can see what I'm talking about. Now, cotangent, you remember, is the reciprocal of tangent. So wherever tangent was 0, cotangent had an asymptote, a vertical asymptote, and vice versa. So there's one cycle of cotangent. Well, that's going to help me understand what happens to the function values as x approaches 0 from the right, but let me get another cycle in here so that we can see what happens as x approaches 0 from the left. Well, we get different things. As we approach 0 from the right with x, the y values go to positive infinity, but as we approach 0 from the left, we're getting y values that approach negative infinity. So let's break this up into cases. Let's do the right-hand limit. And then we'll do the left-hand limit. Now, as x approaches 0 from the right, the cotangent of x approaches positive infinity. Oh, wait a minute. If we have a ratio that has a constant over something that's increasing in magnitude to infinity, we're going to get 0. If we look at the left-hand limit, yeah, the cotangent function will approach negative infinity, but 2 over a denominator that approaches negative infinity is still 0. And since the left and right-hand limits agree, they're the same constant value, we can say, hey, the limit is equal to that value. Okay? Just as a quick reminder, if the limit ever itself equals infinity or negative infinity as an answer, that is a way of saying does not exist. But please remember, you'll be expected to give infinity or negative infinity instead of the does not exist. The only time you'll ever use does not exist to a limit problem answer is if the left-hand limit and the right-hand limit do not end up being the same, meaning the same constant or the same infinite situation. Okay? That's always a bone of contention on the first limit test. Well, that's what I have for you. I'm looking forward to the first day. Again, I will jot down the assignment for the textbook in just a second, and you can find that URL address on the web page, and I'll also put it up here. There you go. There's the book problems and your hyperlink to get to the textbook problems as well. We'll see you in September, as the song goes. We'll see you later.